All right, so what we want to do in this video is continue looking at capacitance, and we want to look at a couple of examples of situations where there are both series and parallel situations, and we want to look at the issues of both using a dielectric in a capacitor, and we want to look at the energy that is in a capacitor. Okay, so let's start with this particular example. Okay, so as it says, this circuit contains both series and parallel components. Okay, so why is this both a series and a parallel configuration? It's because these 2 points right here act like junctions. Okay, so imagine that this is a wire, an external wire, and this is an external wire, and these wires are connected to some larger branch. So suppose there's like a battery right here. Okay. And the battery is then allowing current to flow through the system and connecting to those branches right here. And so then current can flow this way, or it can flow this way, right? And so anytime you have a junction like this, the branch is going to be said to be in a parallel configuration. But these 2 capacitors are in a branch of a wire where the current can only flow in one direction. So, or I should say that there's only one path. Okay. At this junction, it can go either direction, but in this part of the wire, there's only one path. And so these 2 capacitors are said to be in series with each other, and that's why this CS is labeled right here for equivalent capacitance in series. And then that equivalent capacitor is in parallel with the third capacitor, or C3. So C1 and C2 are in series with each other. And that combination is in parallel with C3. So if we want to find what the equivalent capacitance is here, right, we actually have to do all of the calculations explicitly. So remember, when capacitors are in series, we add them with the reciprocal rule. And so C1, C2, or the CS designation is going to equal C1 times C2 over C1 plus C2. So this is going to be 1, this is going to be 5 over 1 plus 5, and the overall unit is going to be microfarads. So this is going to be 5 divided by 6, right? Or 5/6. And in decimal form, that would become 0.83 repeating. So this is approximately 0.83 microfarads. Okay? And so then that combination is in parallel with C3, so the total capacitance would then be the series combination plus C3, which would then be 8.83 microfarads. So the total capacitance here, as you break the circuit down, is going to be 8.83 microfarads. Okay? So, what if we move to this example? And this example is pretty close to the same thing. Okay, actually we have two... it's one situation, but they break it down like they did in the previous one. So, these two capacitors are now in parallel. And once again, the way to tell is that if you have a battery and you have current moving through the battery. Now, we haven't gotten to current yet, so don't worry if that doesn't make a ton of sense yet. Okay? It will. But just know for the moment that the parallel branches are where we have these junctions. Okay? So when you have the junctions with multiple branches coming off or meeting back up, then whatever components are in those two different branches. So this would be a branch. And this would be a branch. And then these two branches meet back up at this junction. Okay? So, what that means is that C2 and C3 are in parallel with each other. And that combination, once you reduce that to an equivalent resistor here, that combination is in series with C1. Okay? So the C2 plus C3, if we label that as, say, C2, 3, in parallel, they're going to just add up, right? They're going to just add up. And once we get that value, whatever those values would be, the total capacitance would be C1 times C2, 3 divided by C1 plus C2, 3. Okay? So at that point you would have to be given explicit values for what the capacitors are, right? But you can work out those numbers if you were given the values, right? A couple of more examples, and as a matter of fact, I might move that slide there. But let's look at these. This particular branch, for circuit A here, is very similar to the one we just saw, right? I have a junction here, and I have a junction here. So I have one path this way, and another path this way. So C2 and 3 are going to be in parallel. Ugh. C2 and 3 are going to be in parallel, and so we make that an equivalent resistor, or capacitor, C2, 3, and C2, 3 is going to be in series with C1. Now, in B, right, we have a junction here, and we have a path, we have a junction and a path, and so C2 and C3 are in the same path, so those are in series. So C2 and C3 are in series, and that combination is in parallel with C1. Now what about circuit C here? So I have a piece of wire here and I have a junction right here. And then I have another junction right here. So I have one path here, I have another path here. And then when I hit this junction, I have another path here and another path here and then another junction. So what this means is that C1 and C2 are in parallel. Likewise, C3 and C4 are in parallel. And the combinations of C1, 2 and C3, 4 are in series with each other. Okay? So that is capacitors in series and parallel. And now we want to address the issue of dielectrics. Okay? So helps when I can spell. Dielectrics. When you put two charged plates in some region of space in this configuration, then they develop or generate a uniform electric field, and we've seen that before, right? And once again, the approximation of a uniform field is really, really good. But when you start to get near the boundaries, you do get these fringe effects, which we ignore for the present case, right? So the field in between these plates is uniform. And remember that the voltage between the two plates can be characterized by the strength of the field times the distance between the plates. Right? V is equal to ED. And likewise, the field strength E can be thought of as the total potential between the plates divided by the distance. Okay? Now, what happens when I put a medium in between the two plates that's not a vacuum, right? When I put a non-vacuum media in between the two plates, what happens? Well, so it turns out that macroscopically, even if you put an insulating material, right? Insulators can still have charges react to external fields. So if I, for example, have a positively charged object, like I've just dumped some positive charge onto a conducting sphere, and I hold that next to a piece of styrofoam. Okay, styrofoam is an insulator. But the attraction from this positive charge will still be such that it rearranges some of the charges inside the styrofoam, and you will get a rearrangement of some of the charge. And so when I put a insulating material inside my in between my two capacitor plates, I get the same kind of effect. So what will this do to the overall field in between the two plates? Well, when you have this particular kind of situation, because the negative charges in the insulating material are going to congregate toward the positive plates, and the positive charges are therefore going to be left to congregate near the negative plate, these produce their own internal electric field this way. It's not quite as strong. Okay? It's not quite as strong. But the overall effect is that the total field E between the two plates is now, if we call this field E of dielectric, then the total field E that the region between the two plates experiences is equal to E naught minus E of the dielectric. Okay? So you've reduced the strength of your field. Okay? You've reduced the strength of your field. Now, why is this important? Right? Why is this important? We characterize dielectrics numerically or quantitatively by the symbol kappa. Okay? So remember that capacitance for parallel plate capacitors had that equation that governed how to calculate the capacitance based on the geometry. So, what we do is insert a kappa into this equation. So the capacitance of your capacitor goes up proportionally with the dielectric strength of your insulating material. Okay? Now, why is this important? Right? Why is this important? This is important because every capacitor has an electric field that after which the field is too strong for the plates to keep adding charge and the field breaks down, or the capacitor itself breaks down. The capacitor may blow, it can fail, and you've exceeded the safety protocols for the capacitor if you put too much charge on it. If you let the electric field grow without bound. So that happens when you apply too much voltage between the plates, because this is also, C is also equal to Q over V. And so once again, remember that Q is equal to CV. And so as you increase the voltage, you increase the amount of charge. But from this equation, we can say that Q is equal to CED. So the more charge you put on the plates, the stronger the electric field. And so if there's a point at which the plates fail because the electric field was too strong, that's an indication that too much charge was dumped, and you put too much charge on it when you put too much potential difference between the plates. So what does the kappa have anything to do? What do dielectrics do? Dielectrics, okay, dielectrics do the following, okay? Remember, this is the expression for the original capacitance. Let's call this C naught. Okay? So C naught is the capacitance for a non-dielectric capacitor. So when you have a dielectric present, this is equal to K times C naught. Okay? And so this is equal, therefore, to Q over V. So Q, when a dielectric is present, is going to be equal to kappa times C naught times V. So for a given voltage, okay, for a given voltage, I can dump more charge onto the plates given a multiplicative factor of kappa. Okay? So dielectrics allow you to put more charge on the plates for a given voltage without reaching a breakdown in the electric field and causing your device to fail. So the dielectric serves almost both to increase the efficiency of the capacitor and allows you to put more charge on it before it would fail. So, what are the typical values of dielectrics? Well, some typical substances that are used are things like paper, which has a dielectric constant of 3.5. Polystyrene has a dielectric constant of 2.6. Water, if you use water, you actually achieve a dielectric constant of 80, right? But that's a pretty difficult capacitor to build. So most of the time they would use things like paper or some other rather cheap dielectric that wouldn't cost a lot of material to build and insulate like water would, right? But the bottom line is that most materials that you would use as a dielectric constant have kappas greater than 1. The kappa for air is approximately 1, and most other dielectrics are larger than 1. Okay? So, that is why we use dielectrics. Next, what we want to talk about is the energy that is stored in the electric fields with the capacitors. So, anytime you have electric fields, you have energy. Okay? And we'll find the same thing with magnetic fields too. Anytime you have magnetic fields, you have energy. So, how much energy is in the field of a parallel plate capacitor? Well, let's find out. So, remember that work is equal to QED. but this is the same thing as QV. And so, if I want to look at an infinitesimal snapshot of what's happening when I have a parallel plate capacitor connected to a battery of potential V, okay, the infinitesimal amount of work to pull an infinitesimal amount of charge off of one of the plates and deposit on the other one is going to be dW, and that is then going to be dQV. Okay? So that's the amount of work that it takes to pull an infinitesimal amount of charge at some voltage. Now, remember that Q is equal to CV. And C is a constant. Again, C is just based on the geometry of your system. So, if I want to obtain an expression for dQ, this is then going to be C dV. So, the V here, okay, is the voltage across the plates. Now, in this particular circuit, as I've mentioned, it happens nearly instantaneously by human standards. Our clocks, at least our basic stopwatches that we have on our iPhones and things like that, are way too imprecise a device to measure this. It is practically in the blink of an eye that the plates are charged. But each individual charge does have to move. And so microscopically, if you could slow down time several million times, you would actually be able to see the charges on the plates leave one of the plates and the charge gather on the other plate. So V is not constant while the plates are charging. Okay, V is not constant while the plates are charging. So what that means is, for the total amount of work, I can insert this expression in for dQ and get CVdV. So if I want to get the total work, I can integrate. And I would just simply integrate from 0 to the total voltage of the battery, and that's going to give me the total amount of work, which is equal to 1/2 CV squared. So this formula should harken back some memories, right? This formula should harken back some memories. 1/2 CV squared. This should remind you of kinetic energy. 1/2 mv squared. Now the V's here are different things. The V here is potential, and the V in kinetic energy is velocity. But what is true is that the form of the system is the same. Remember that in kinetic energy you had 1/2 mv squared, and in kinetic energy you have the 1/2, you have 1/2 here. M is a constant of the system, or what we would call an inherent property. Okay, the masses of objects don't change. Okay, now you can have a system where mass is variable, such as rocket propulsion, but if you think of the rocket as two separate pieces, the fuel and the fuselage, then the fuselage doesn't change mass. It's only because it's losing fuel that the overall system is lighter. But in our sense, mass is a constant. And the velocity is a variable of the system. The mass can be traveling with whatever velocity you choose. It doesn't have to be a set value. So you have 1/2 times a constant times the square of something that's not constant. You have the same form here. You have 1/2 times a constant of the system times something that you can choose. You can set the voltage to be whatever you want, right? As long as you have a battery of a given voltage, you can set the voltage to be whatever you like. So you have 1/2 times something that's constant times something that doesn't have to be constant. You can set the voltage to be whatever. So they followed the same form, and this is very common when we talk about energy. Energy will often follow this type of form. Okay, so if we look at a capacitor, and by the way, this represents, right? This represents when you talk about work, the magnitude of work is also the magnitude of the potential energy. Okay? So when you have a parallel plate capacitor that is fully charged, that capacitor has potential energy of 1/2 CV squared. Now this is an incredibly important result. Why is this an important result? This shows that electric fields have energy. This will become very important down the road. Okay? Electric fields have energy, and this will become very important down the road. We can take this a couple of steps further. Okay? We can also rewrite this because we can reinsert the definition of capacitance in here, and remember that V would be equal to Q over C, right? So if you insert that definition, this is equal to 1/2 Q squared over C. Okay, so these two forms are exactly the same. They give you the exact same amount of energy. And so if you know the capacitance and the potential, or if you know the charge and the capacitance, you can get the total amount of potential energy in joules. If your charge is in coulombs, if your capacitance is in coulombs per volt, and your potential is in volts, then you can get your energy in joules. So, for example, right, if we come back up here, and let's say that the charge on the plates was 3 microcoulombs, okay? And let's just, for example, say that the capacitance, let's say that this is a 12 microfarad capacitor. Okay. So, what would be the energy in this system? Okay, what would be the energy in this system? Well, given that we have Q and C, then I would want to use this form. Okay, and so this is going to be 1/2 Q squared over C. So this would be 1/2 Q squared, 3 microcoulombs squared, over 12 microfarads. So 12 divided into 9 is 0.75, right? And then you're cutting that in half. So 0.375. Yeah. So 0.375 microcoulombs or microjoules. Okay. 0.375 microjoules. So by typical standards, not a ton of energy by microscopic standards, but by microscopic standards, that's quite a bit, right? If you want to kind of convince yourself what kind of energy that is, then I would invite you to do the following calculation. Allow a proton to sit here and calculate how much or what its speed would be if you released it from rest and it accelerated toward the negative plates. Calculate what its final speed would be. Okay, so how would you do that? Well, you can use this formula, 1/2 QC squared, or 1/2 Q squared over C, to solve for the voltage from the energy formula with the voltage in it. You can solve this formula for V, and you know that V is equal to energy per unit charge. So the change in potential energy would be Q times V, and that must be, if you change your potential by that much, that must also be the change in kinetic energy. So if you know the mass of a proton, which is 1.67 times 10 to the negative 27 kilograms, you can equate QV to 1/2 mv squared and solve for the velocity. Okay? And I would invite you to do that. It might be an instructive exercise, right, to be able to do that. The last thing to mention in relation to capacitors, one thing to note, okay, so first things first, we want the overall thing that we want to talk about is energy density. All right. So what is energy density? Energy density is not the total energy between the plates, not the total energy between the plates, but the energy divided by the volume between the plates. So remember, you're seeing the plates edge on, right? You're seeing the plates edge on. But in a true parallel plate capacitor, they have some area to them. So if I drew a block of unit volume that, I'm going to fail at this miserably. Yeah, I'm going to fail at that really, really badly. How would I want this to look? Let's see if we can do it this way. If I have a block, okay, and I let this block be unit volume, then how much energy is in that unit? So what I would do is I would find out how many unit volumes I had by calculating the volume between the plates, or that would be the same thing as the area of the plates times the distance d between them. So the volume is going to be the area of the plates times the distance between them. Okay. So that's what energy density is. Energy density is the total amount of energy in a unit volume. Okay. Now, remember that the capacitance of a parallel plate capacitor without a dielectric is given by epsilon naught A times D. But capacitance is equal to Q over V. So this is also then equal to Q over V. And what we're wanting to do, okay, what we're wanting to do is express the capacitance in terms of the electric field, okay, because the electric field is a fundamental quantity. And so if we can describe our system in terms of that electric field, it's something that we can measure and or calculate in many different circumstances. So it is going to be a fundamental quantity of interest. So that's what we want to do, is we want to get this in terms of the electric field. But remember that the electric field is related to the voltage through this formula, right? So if I take the reciprocal of both sides, I'm going to get V over Q is equal to D over epsilon naught A. And then if I divide both sides by D, so I'm going to put the D down here, and I multiply both sides by Q, so I put the Q up here, then I'm going to get V over D is equal to Q over epsilon naught A, right? And V is related to E through V equals ED, so E is going to be equal to V over D. So this side is my electric field. So E is equal to Q over epsilon naught A. If you have a parallel plate capacitor and you know the total amount of charge and you know the separation, or the area on the plates, you can calculate the electric field. Okay? So, with that in mind, if you come back to, we're going to use this momentarily, okay? And not to confuse anything, get rid of those arrows. So the electric field is Q over epsilon naught A. And remember that the energy is equal to 1/2 Q squared over C, right? But again, C is equal to epsilon naught A over D. So this is going to be equal to 1/2 Q squared times epsilon naught A over D to the -1, or 1/2 Q squared times D over epsilon naught A, or Q squared D over 2 epsilon naught A, right? But the volume between the plates, right, going back up here, the total volume between the plates, the size of this box right here, the large box right here, the total volume is going to be the area times the distance. Okay, so the energy density, or the energy per unit volume, is going to be, well, okay, so let's see where we are right now. We've got Q squared D over 2 epsilon naught A. The energy density is going to be equal to, okay, equal to, we give it the lowercase u, and we're going to give it the subscript E for electric energy, not to be confused with magnetic energy when we get there. But this is going to be U divided by the volume. Okay? So this is going to be U divided by AD. And so if I take this expression and I divide that by AD, I'm going to get Q squared D over 2 epsilon naught A times 1 over AD. Okay? But that's going to cancel with that. And so now UE is going to be Q squared over 2 epsilon naught A squared from the A times A. But we can write Q squared in terms of the electric field. So, because it's easier to measure things like potential and electric field than it is total charge, that's why we want this in terms of the field, because it's easier to measure than it is to count the number of charges. Okay? And so, if I square that and insert it into my equation, Q is going to equal epsilon naught times the field times A. So Q squared is going to bring squareds everywhere. So this is going to be epsilon naught squared E squared A squared times 1 over 2 epsilon naught A squared. So the a squareds cancel, one of the epsilon naughts cancel, and I'm left with one of the epsilon naughts, an e squared, and a 1/2. So the energy density in terms of the fields turns into 1/2 epsilon naught e squared. Okay? 1/2 epsilon naught e squared. So that is the energy density in a parallel plate capacitor. And it actually turns out that this is the energy density. This particular expression is valid universally anywhere that there are electric fields. Electric fields are carriers of energy. I cannot stress this enough. This is going to become very important down the road. But electric fields carry energy. And the energy density in that field, or the energy per unit volume, okay, the energy per unit volume is going to be equal to 1/2 epsilon naught e squared. Now, something that you should find, okay, some common sense checks. U is often going to be very small, as we found from here, okay? If you have things like microcoulombs and microfarads and capacitance, your overall energy is usually going to be on the order of something like millijoules or microjoules or nanojoules or something like that. The total amount of energy is usually going to be very, very small. Your energy density, on the other hand, can be very high. Why is that? Well, it's because capacitors are usually very small, but the unit of volume in the SI system is the square meter. So if I have a capacitor that has, for example, say 1 microjoule of energy in it, but it's 1/billionth of a square meter. Actually, I mean, that'd be really, really small. But maybe 1/millionth of a, cubic meter. Okay. If you could fit 1 million capacitors in a cubic meter, then if your energy is 1 microjoule, then the energy density would be 1 joule per cubic meter. So you can have a very high energy density compared to your energy, typically, especially for capacitors. It can be on the order of millions, billions, or sometimes much more, right? Depending on the size of your capacitor and the amount of charge on it and so on. But typically you can fit, hundreds to thousands to millions of capacitors in a cubic meter. And so therefore your energy density, or the energy per unit volume, is going to be very, very high comparatively. Okay? It can be very, very high comparatively. So, with that in mind, that is capacitance. And I hope you guys have found this lecture informative. And if you have any questions, let me know.